So now we are going to um, start looking at taking limits without relying on our calculator. And maybe a way to say this is taking limits efficiently without a calculator. And so one of the best or starting point places you should do is actually just try direct substitution. Like, remember, a limit talks about the behavior of the function near a point, right? Not at the point exactly, but near the point. But sometimes direct substitution can give you an idea of what's happening a bit, give you some clues. So if I try to put -1 into this function, I get -1 plus 1, which is 0. And I get -1 squared, which is 1 minus 1, which is also 0. So I know that I don't know what the limit value is, but I do know that there's a hole, and a hole can be fixed. And so one of the ways that we can remove this hole is to factor. And we even looked at this last semester in rational functions. Now, whether you have me or Mrs. Moore next year in calculus, you really need to be meticulous in this limit. So I'm going to have to keep my limit, because that's what I'm ultimately solving for, as x approaches -1. And then x plus 1 stays on the top. But in the bottom, I can factor that to x plus 1, x minus 1. And now, I notice that I have two factors of x plus 1, one on top and one on bottom. Now, think about when x is -1, this factor here represents a 0, and this factor here represents a 0. It's this 0 over 0 that is sort of preventing us from knowing what does this function look like. Well, if we remove that 0 over 0, we will get at the limit, since we haven't taken it yet, so we have to still write this, as the x equals -1 of 1 over x minus 1. Now I can directly substitute -1 into this function, and so I get 1 over -2, which is the limit value. That would be what the function would behave like as we get closer and closer to -1. So factoring is a really good tool. Doing that direct substitution to see if you do get 0 over 0 tells you that there's something else going on, that you need to be able to fix that hole. So, again, just by inspection, I can see that putting a -3 in the denominator gives me 0. -3 squared is 9, minus a -3 is 12, minus 12, so I get 0 over 0. So I know the behavior of this function near -3. There's a hole, and I want to see if I can figure out what the y coordinate of that hole is. What is happening as we get closer and closer to that value? So I'm still going to have to write the limit as x approaches -3, and we can factor the top to x plus 3 and x minus 4 over x plus 3 times x minus 3, since it's a difference of squares. And again, if I think about the factor of putting -3 here, this is the 0, this is the 0. So we're sort of removing that 0 over 0, and we're getting a function that we can then evaluate. It's simplified. And so then let's go ahead and rewrite that. So it's the limit as x approaches -3 of x minus 4 over x minus 3. Now I can put in -3, and I get a -7 in the numerator and a -6 in the denominator, or a value of 7/6. Okay. Part B as well. Feel free to stop the video and do it on your own. But if I try to put in 2 cubed is 8, and 8 minus 8 is 0. 2 squared is 4, and 4 minus 4 is 0. So again, there must be a hole here. So let's do the limit as x approaches 2. Let's factor. And so bottom difference of squares is probably easier to remember. Top is a difference of cubes, so it's going to be x minus 2. And then if you remember the SOAP, right, same opposite, always positive. So x squared, opposite, so plus 2x, and then always positive, plus 4. Now you can always check to make sure, like -2 times 4, there's your -8. -2 times 2x is a -4x. Yeah, no, sorry, it's a negative 4x, and then here is the positive 4x to cancel it. Here's negative 2x squared. There's the positive 2x squared to cancel it as well. Okay, so then again, we remove the 0 over 0, so x minus 2, and then we can go back and say the limit as x approaches 2 of x squared plus 2x plus 4 over x plus 2. We put in 2. 2 plus 2 is 4 in the denominator. 2 squared is 4 plus 4 plus 4, which is 12. So 12 over 4, which is 3. Okay, excellent. Now, I want to jump down to another example here, number 4. Because here, when I try to directly put in 7, 7 minus 3 is 4, the square root of 4 is 2, 2 minus 2 is 0, and then 7 minus 7 is 0. So I have another hole. I have another discontinuity that I'm going to try to remove. And factoring is really not the way to go here, but if you remember something that we looked at last semester, when you have square roots in a rational function, you want to multiply by the conjugate. And in this case, it doesn't really matter where the square root appears, whether it's the numerator or the denominator. So, but it gets a little tedious of writing, monotonous maybe. So the limit as x approaches 7. Excuse me. So the original problem was the square root of x minus 3 minus 2 over x minus 7. So what we're going to do is multiply by the conjugate on top and bottom. And so the conjugate, you're just changing that sign. So it's going to be the square root of x minus 3 plus 2 on the top and the square root of x minus 3 plus 2 on the bottom. Okay, so we still haven't taken the limit yet, so you need to write that. Okay, I'm going to look for that. If you're in my, like I said, if you're in my class or Mrs. Moore's class next year for BC, or even for AB, for that matter, make sure you do write those functions, or those limits. Okay, so root x times root x, those cancel, so it's just x minus 3. And then the beauty of the conjugate, there's positive, there's negative, and so then we have minus 4 over. Now leave this factor. Don't distribute, because honestly, nothing good is going to come of that. I mean, there's nothing that could be simplified. So we're going to do this. And notice this x minus 3 minus 4, that is x minus 7. So I'm going to, again, show my step here, show my work. X minus 7 over x minus 7 times the square root of x minus 3 plus 2. Okay, so now, again, thinking about removing that 0 over 0. Like x minus 7, that's the 0 over 0. So now I have a simplified version of this function. So limit as x approaches 7 of 1 over the square root of x minus 3 plus 2. Right? So then as x approaches 7, 7 minus 3 is 4, square root of 4 is 2, and then plus another 2 is 4, so I get a value of 1/4. Okay, now next year in calculus, we will prove these. And one of the things that I've always put into like this class is starting to do, starting to look at trig limits. And so one of the limits that we'll prove using something called the squeeze theorem, which is pretty cool. It will show that next year. But for now, just the limit as x approaches 0 of sine of x over x is equal to 1. In fact, we even looked at that yesterday, or when I recorded the notes yesterday on our calculator, and we looked at that table of values. So that's something that I'm encouraging students taking A, B, or BC next year to memorize that to be 1. And then this one, again, we can prove by the squeeze theorem is equal to 0. And see, the thing is that like if you let x be 0, right, so 0, so you do get the sine of 0 over 0, which is 0 over 0. So I know there's a hole. But the thing is that we can't factor this, and we can't multiply by a conjugate. And there's other techniques that we're going to learn in calculus to help us to help us find this answer. But the technique in terms of what we can do right now today is look at a table of values and look at the behavior of the function from that point of view. Same thing here. This is another 0 over 0. But if you look at the behavior of this function on a table of values, you would see that its limit value would equal 0. Now, there's a couple other things I want to do. I'm going to jump to number 6. And actually, I've added more problems to my number 6 than you, so please write these down as well. And the thing is that like the AP exam tries to, like if all we ever looked at was like sine of x over x as x goes to 0, like that's like you're not really applying anything. But now take a look at what if you start having other sorts of functions going on here. So you kind of want to just manipulate it a bit to make it look like this, make it look like sine x over x. And so I can kind of separate or think separately, like, oh, well, this is the limit as x approaches 0 of 3, and there's like sine of x and like 4x. Like you're just multiplying, but if you think about like the 3 times that and the 4 times that, then I do in fact get this sine x over x. So that much of the function is going to approach 1, and then we just have the coefficient of 3/4. So I'd have 3/4 times 1, which is equal to 3/4. And the thing is that you can do that for like, even when like here, like sine of 5x over 6x. So I'm trying to make these, like this angle, equal this value down here. And so one way to do that is to say, okay, well, this is the limit as x approaches 0, sine of 5x. So we really would like a 5x down here. Like we'd like that to match. There was already a 6 that was down here. Right? So this is what we'd like. So we'd like a 5x there because we want those to match, whether they're called 1x or 2x or 3x or 4x or 5x. So the thing is, if I put a 5 here, I better also put a 5 up here so that I can balance it. It's like you're multiplying by a fancy 1. And so if you take a look, this 5 and this 5, like those are what I've kind of inserted, kind of help me out in terms of the structure. Sine of 5x over 6 is what I was given. Here's the 5 over 5, which is a fancy 1. Well, that's great. So now I can look at this much of the function. Go to red here. So this much of the sine 5x over 5x, that approaches 1. And we just have the coefficient of 5/6. So we get 5/6. And you're going to get really good at this, and you're going to realize that ratio of 5/6 is just sitting right there, right? So, and I'm anticipating like the same thing. It doesn't matter if it's in the denominator or the numerator for the sine function, because if you go back to this up here, that limit's equal to 1. So the ratio, the reciprocal of 1 is still 1. So I'm anticipating this to be 1/2 because it's a 5 to 10 ratio. And here's what I can do. If I want a 10x down here, or as an angle, what I might do is I might multiply the top by a 10, so I can have a 10x and multiply the bottom by a 10. So that 10 over 10, that's a fancy 1, right? And the reason I picked 10 is because that was the part that was in this angle. So now, again, thinking about this is the limit as x approaches 0. I'm going to think about like putting the 10 with the x. So I have a 5 times 10x. And in my denominator, I have a 10 times sine of 10x. So you could always do this. And here I have the ratio of a 1, as long as whatever's inside this angle is the same as up here. So the 10x over sine 10x, that's a 1, and then 5/10, which is 1/2. Which is excellent. Now, tangent I threw in here too, and tangent of x really is just sine x over cosine x. So if I think about the limit as x approaches 0 of, okay, if I rewrite tangent as sine over cosine divided by x, like that, and then that could be rewritten, since this is like a complex fraction, I could write that as a limit as x approaches 0 of sine x divided by cosine x. And then instead of dividing by x, you multiply by the reciprocal, 1 over x, which is equal to the limit as x approaches 0. Hopefully you're doing better at managing your space than I am. Sine x, cosine x, 1 over x. So just kind of grouping that using the associative property. Here I can put the sine x over x, and as long as I'm approaching 0, this much right here is equal to 1. And then as x approaches 0 here, you get cosine of 0, which is 1. So this much also is 1. So my limit value is 1. And so a lot of times students will remember that tangent of x over x behaves a lot like sine x over x, because the only difference is that you have a cosine of x in the denominator, which creates your which creates your tangent function. But think about, as x approaches 0, cosine approaches 1. So it becomes, it becomes, it doesn't affect it. I'm trying to think of a word. It becomes, it doesn't help determine what the behavior is. I'll think of the word. And the thing is that like this tangent of 4x over 2x, I can start looking at that ratio and that, oh, it's a 4:2 ratio. Fantastic. So I know my answer probably should be 2. And again, you can think about that. If I wanted a 4x, I need a 4x down here. So then I'm going to multiply by 4 over 4. So then I could say, oh, so this is the limit as x approaches 0. I'm going to just put that first 4 in front. So 4 tangent of 4x. And then I want this 4 and this x to be here, which means I have this 2 left over. So as long as I can write it and think about, like, okay, here it is. Here's tangent of 4x over 4x. It's the same angle over the same ratio. So that much is equal to 1. And then 4 over 2, which is 2. So our limit is equal to 2. Okay, so, there's a lot of trig on the AP exam, which I'm excited about to see this year. My kids are taking it next week. And then there's one more example. Let's finish off our notes with this last example here. I'm going to do some erasing here, if that's okay. So sine squared and x squared. So you want to think about sine squared and x squared literally as like sine squared is multiplying sine by itself. And so I'm going to rewrite this first as saying it's the limit as x approaches 0 of sine of 2x times sine of 2x. Like that literally is what sine squared means. And then x squared is x times x. And so what ends up happening is you have two limits together. So this much that I'm circling first, that's like a 2-to-1 ratio. So that part of the function will approach 2. And then this much right here is another 2-to-1 ratio, so that'll approach 2 as well. So our limit value is going to equal 4. So I thought those are some good problems to kind of start us off with looking at how do you find limits that are 0 over 0 without a calculator. And we went through 3 methods, right? We went through factoring, we went through multiplying by a conjugate, and then we went by looking at some trig identities that we need to know. And really the big one that you need to know is the sine x over x. And that tangent's going to behave like it. Sine x over x is great. And then every once in a while you might see that 1 minus cosine x over x that we looked at the last notes, which is approaching 0. So I think what I might do is maybe do one more video. We'll see about more limits, but keep looking at the practice questions on Canvas, and send me an email if you do have any more questions.